So I'm just going to start with the LT Spice model. So here we have, I'll just zoom in. Rid of that. So our R1 13k ohms, R2 5.6k, our this is C1, but and this is 0.1 microfarads, and a C2 of 3.3 nanofarads. I have the step set up here with Tran. So if we just click run, and then if I click, I think this, we can see if we just zoom in, the green there is the step up to, I set it to 200 millivolts, so it goes up to 200 millivolts at 1 second, and then you can see in the blue the step response. You can zoom. So if we then go into our MATLAB, I tried this before, but let me just clear for now. So first of all, we're going to take in the step response from the LT Spice. So I have, just purely for the function of the video, I'm just going to copy and paste the directory. So audio read. Oh, I already have it. And get rid of that. So there's our step response input. Because it was only up to 200 millivolts, I'm going to make it up to the 1 volt that a normal step response is. So I'm just going to times it by 5. Step response. So there's that. So again, we're just going to set up the time on the x-axis, 0. Make sure that was 0. 0 to the length. Oh wait, I don't. Sorry, 1 sec. Doing this wrong. I need to set up the impulse now. So we say impulse response. Response is equal to the derivative of the step response. Then we get the I clicked something there. Then we get the absolute value of it for when we plot it. So it's ABS FFT of the impulse response. Then we set up our time, so I'm just going to call it fax is equal to 0 to the length of x minus 1. Then that's all going to be divided by the length of x times that. So then if we plot fax x there's that, and then I just want to make the semi-log x fax 20 log 10 of x. So there we go. So here's our impulse response. We ignore this, and here we have the impulse response. So now that that's done, I'm going to do that using the BNA coefficients. So I'm going to set up a step response with the BNA, and then the arbitrary input. So we have to create our num is equal to, for the purpose of this, I'm going to copy and paste these numbers because it will take too long otherwise. There's our num, and then so of course our first value is going to be 1, then our next value is this, the coefficient of the s, and our last value is this. Oh, I might be doing this wrong. It did. I don't know what this is about. Might just be that. Okay, I'm not sure why it's not working. I'm just going to, hopefully this will work. There we go. I'm not sure why that wasn't working, but I just want to get this done. So then we set up our system. So sys1 is equal to the transfer function of num and denum. So then if we type like sys1, we should get out our transfer function. So then if we just say step of sys1, we should, and we get our step response. Very simple. Now, the last thing I want to set up is the arbitrary input. So we're going to have our IP fs is equal to audio read. Oh, no, not that. Again, I'm just going to copy and paste. I believe I have one here. It's just a random signal from the files online. So this is going to act as our random input. So then I'm just going to, I believe our sys1 is still set up. So if we change our t is equal to the 0 to the length of IP minus 1 and then divided by our fs. And then if we y is equal to L sim sys1 IP t, and then we just say plot y. I believe that should work. So yeah, you can see the that's after the filter. So we input a signal wave, we filtered it using the transfer function, and that was our output. So if I just I think it might work if I x is equal to that, and then if I say plot x, we can just see the original, possibly. Yeah, so there's the original. So the one before, you can see, is a lot more filtered. You can, it had this distinctly the sound, each of the words that were said, and it's a lot more filtered. It doesn't have any of the high frequency noises. So yeah, that was each of the requirements, and of course then the LT spice and everything. I'm just gonna